Okay. Okay. So first, I'd like to thank the organizers. It's really a privilege for me to speak at this conference. What I want to talk about is periods of automorphic forms. And as I wrote the title, I'm a phrase that most people have never heard. It's the kind of piece of the language program which I think doesn't have the publicity it deserves. So, and it's seen a lot of development in the last 20 years. So a large part of my talk is just to advertise that, which is the work of very, very many people. So I'm going to start the talk with kind of some toy examples. So let me tell you first where I'm going. So I'm going to say, I'm going to give sort of a crash introduction of automorphic forms, but later. But what are periods of automorphic forms? They're numbers you extract by integrating them over certain special cycles. So I'll say what that means. And in this talk, I'm going to distinguish two types of periods of interest. One are automorphic, one are cohomological. I mean, this is just my terminology, it's not a standard one. Automorphic periods are what people, I think, usually refer to as periods of automorphic forms, and I'll tell the story of how these are related to L functions. And one way you can think of this is kind of a generalization of the Kamigawa number story, which told by Jacob and Dennis. So that's not a very. So I'll use that at least as a metaphor a couple of times to understand what's going on with these periods. And then at the end, I'm going to speculate a little bit about cohomological periods and their relation to motivic cohomology. Okay, so but the first part of the talk, I'm just going to give some fairly simple toy examples to illustrate. So these are meant to illustrate the more general setting that comes later. Okay, so the examples that I'm going to give, I'll just say what is in common about them before I actually give them. So they're all about L functions, and for the purpose of this talk, you can understand L function to be anything which looks and smells like a Riemann zeta function. So that is to say, here's the Riemann zeta function, part of n to the minus s. By the way, in this talk, I have to apologize, I'm going to be not very good about putting subscripts of summation because it would cover up various things, but hopefully in most cases it'll be clear from context. So an L function just means you put coefficients in, but it should have the following three basic properties, which were essentially known to Euler, at least in some form. Firstly, the zeta function factorizes as a product over primes. Secondly, it has an analytic continuation, say it can make sense of it even when the series doesn't converge. And thirdly, it has a functional equation. That is to say, there's some symmetry between the values s and 1 minus s. So the example I'm going to say, it's not going to be immediately clear, all share these properties. Okay, and that's their common thread, and this notion of L function is going to play an important role. All right, so here's the first formula. So I'm going to give a list of formulas, and we're going to discuss some ways of proving them, and then those ways will be toy models. So this was found by Euler. The sum of the value of the zeta function at 2 is pi squared over 6. And he also found the values of all even integers can be similarly expressed. Okay, so this, you have some reciprocal k tars, where k is even, then you could write it as the corresponding power of pi times a rational number. Okay, now let me give a sort of the simplest, I would say, non-trivial variant on this story, which is to alternate signs. Okay, if you just alternate signs, you get that really is easy to express in terms of this, but if you just restrict the odd numbers and alternate signs, you get something that behaves a little bit differently. So this series is very easy to check for yourself because it's the Taylor series of the arctangent, evaluated at 1. maybe not so well known is that there are corresponding formulas for odd powers. Okay, so if you put in the same series but with odd powers, you can again express them as the same power of pi times a rational number. So those are the formulas for 3 and 5. Okay, so these are null functions. Now let me step up to a slightly more complicated example. And the easiest way, I was tempted to give many examples here, but I'm just going to stick to the simplest one that makes the points I want. The simplest thing we can do is we can look instead at integers, we look at Gaussian integers. Okay, and then I'll write you guys something, I would say, significantly more subtle. Okay, so, all right, so Gaussian integers means integer plus I times integer, like 2 plus 3i. And we can do the same things, exactly the same thing with powers of Gaussian integers. So here's the sum of reciprocals of fourth powers of Gaussian integers. 3.15, 1, 2, 1, 2, and so on. And so this one is not a power of pi, and it was what it was computed by Hurwitz. Give me the following formula. It's omega to the fourth over 15. This omega is the integral from 1 to 0 of dx over square root 1 minus x to the fourth. Okay. And, all right, so I'm going to use it a few times in my example, so stick it in your mind. And just to make the parallel with the first slide clear, in the first slide there were pi's on it, and those pi, you could think of pi as being given by almost the same formula. Let's get that 4 replaced by a 2. Okay, and here again, there's a similar pattern when you start increasing the exponent. Okay, so when you make the fourth powers, the same thing. By the way, if you look at, say, squares or 6 powers or so on, the other values are 0 for trivial reasons, and that's the only reason it's multiple of 4. So, okay, you have the same story here. So this rational numbers times powers of omega, and that's kind of a more interesting phenomenon. But qualitatively the same. And let me finish with one more example along that line, where I'm going to, so to speak, an alternating sign version of this. Okay, so for the zeta function, I looked at odd, summed over odd integers and alternating signs, and then back to the formulas. Here, the analog, it's not clear what the exact analog is, but here's one thing which I think is a fair analog. So here I'm summing over odd Gaussian integers. What that means is the absolute value squared should be odd. And now, rather than just signs plus or minus 1, I also put plus or minus 1 and plus or minus I. Here's the rule to select the sign. You can ignore it. It just says in some sense that it alternates in a period. It rotates in a periodic fashion. So, okay, well, so what are we doing? So you should think of this as kind of an analog of 1 minus a third plus a fifth minus 7, so on, as pi over 4. This one is not convergent, but it's not a big deal, so. Okay, and then there's a similar story. You can start raising this to odd powers, and you will have exactly the same kind of story as we did. Okay, so there's certainly a story behind this, but what I want to do is just talk about how we might go about proving some of these identities. And so what I'm going to say is not even the simplest way, just the way which is most appropriate for illustrating what's coming next. So in these cases, one way to prove it is you can find a way to regard these theories as specializations of a holomorphic or a meromorphic function. Okay, so to illustrate what I mean, the sum of reciprocals of squares, you can try to compute that by adding a variable z, so you sum over 1 over integer n plus z squared. And here now, in that sum, I really want n to go over all integers. And this is now, it's a holomorphic function of z. But it's not very hard to guess what holomorphic function it is because it's periodic in z, so it seems likely it should be a trigonometric function. And if you have some guess as to which one it is, you can check it just by checking that it has the same poles and the same behavior at infinity. Okay, so somehow these holomorphic functions are very rigid. And then you can recover what you want by specializing z to 0. So you can do the same thing in the Gaussian case. Now, here there are multiple ways you could think about doing this, and the way I'm doing it is I think, not the simplest one, but we can treat I as a free variable z. Okay, so instead of I, make this a function of z, and so what we want is a specialization of this in I. One nice thing about doing this, just cosmetically, is that you also, if you let z go to infinity, you then just recover sums over ordinary integers. Okay, that's not just a nice thing. Right, now this function g, similar to the case above, is well, not only is it periodic, but it has further transformation properties. So it's periodic, that is, if you send z to z plus 1, it doesn't change. But also because of this double summation, it's easy to see it has further transformation properties, which make it into a modular form. That is, so g of z is g of z plus 1, but it also has some transformation property under inversion. Okay, so it's some kind of highly symmetric function. And one way to express those symmetries is to say that this, if you formally multiply it by dz squared, so you have this quadratic differential, this is actually literally invariant under all those transformations I said. Z goes to z plus 1 and z goes to minus 1 over z. And so this function descends to some quotient. So the series is convergent off the real axis, but let's just look above the real axis. This object descends to the quotient of that upper half plane by the group generated by those transformations. And so this quotient is called the modular curve. Okay, we'll see it later. And all right, so this is so this series I wanted, I can now understand it as a specialization of this function g4. Right, now that doesn't answer the question how you make it related to omega, and I'm not going to do that. I'll just say a couple words, which is that again, now it's in this nice rigid world of holomorphic functions. If you have to make up some other candidate, more algebraic object, and you can then check it's equal to G4 by checking that it has the same general behavior. So you can interpret this as moduli of elliptic curves and then identify G4 in some other way. Okay, that's how you show it's equal to omega. But all I want really is this formula. Okay, this formula will be an example of the type of thing which I'm trying to explain later in the talk. All right, now let me do a second example. Okay, so this example, I had this zeta-like thing, which is a special value of a modular function. It's a value at a specific point. There are other identities of this type, and where rather than evaluate at a point, you integrate something. Okay, so now to illustrate that, I'll use that alternating sign version of the Gaussian. So, okay, remember, this is sum over odd Gaussian integers of these phases that are either 1 minus 1i or minus I in some alternating way. So in order you can evaluate it, this thing, well, there's more than one way, but one way you can do it is you can compute it as an integral of something over the modular curve rather than as an evaluation. Okay, so the formula will not be enormously meaningful if you're not familiar with modular forms, but whatever it is, it's some function of z which will be the same sum over Gaussian integers chi of alpha over alpha times something. Here's the something, it's some exponential. Okay, so the details aren't important, but this function of z descends. It's defined when z is in the upper half plane, and it has exactly the same type of extra symmetry that makes it descend to this modular curve. So it's similar to that G4 that we saw earlier. Okay, so what? The series we want, you can then express as the integral from 0 to I infinity of this h of z dz. And that's an elementary, the non-trivial thing so far is that it descends. Okay, the fact that this integral left and right hand side are equal is elementary because you just do it term by term. Okay, how does that help you? It turns out, okay, again, this last sentence is not at all transparent, but it turns out that this, I've called it M, this cover of the modular curve, you can make a holomorphic map from it to the genus 1 curve y squared is x to the 4th minus 1. And using that map, you can kind of fold the left-hand integral into this dx over square root 1 minus x to the fourth. Okay, again, the details of that last step, that's how you get to this omega from this point of view. So there are many things there which kind of not apparent at first glance. But what I care about is this formula. So I'll call this formula example B, and the previous formula involving G4 example A. And sorry, it occurs to me now that I may have used, in the rest of the talk, I may use omega to refer to this differential form, capital omega. But anyway, so here are two examples where the value of some zeta-like series is expressed as either a value or an integral of a modular form, and then you can use that to somehow explicitly evaluate them. Yeah?
So 0 and infinity are different cusps?
In this case, they're different cusps. Yeah. Okay, now, unfortunately, the purpose of this talk is not, these identities as a whole story, which is a very beautiful story, but that's not kind of the purpose of this talk. But so that you know, all the examples I said, there's a general conjecture due to Bailenson and refined by Bloch and Cardo, which predicts what values of, so to speak, L functions of arithmetic origin at integer points are. Okay, and all the formulas I wrote down at the start are special cases of that conjecture. So there's much more to be said, but I'm going to move on to the automorphic periods. So before I talk about automorphic periods, I have to say what automorphic forms are, and I'll give a bit of a slightly primitive definition, which is enough for us. Okay. So if G is a reductive group over Z, and for the purposes of talk, if you just substitute SL2 or GLN every time you see G, that it won't be such a big loss. Associated to that, there is a Riemannian manifold. Okay, so this Riemannian manifold it's a kind of the quotient of the spaces that Matt Emerton was talking about, but you can. So I'm going to use a slightly cruder definition of automorphic form. So what it is. So the group, if you take any such group, there's a symmetric space attached to the real points. So it's a Riemannian manifold. And you can quotient it by the integer points. Okay, so whatever it is, this is a Riemannian manifold. It has a at least up to scale, more or less canonical Riemannian structure. That's all. It's some sort of canonical geometry associated to this group over the integers. And one example we've seen before, which is that for SL2, this Riemannian manifold is that modular curve that I showed earlier. That is the upper half plane quotiented by fractional linear transformations. And in that case, that has some kind of extra structure. So it has a Riemannian structure, which is that it carries a metric of constant negative curvature. But it's also identified with the complex points of the moduli of elliptic curves. Okay, so in general, there's no such luck. We just have to be grateful that it even has a Riemannian structure. So for example, for GLN, when n is bigger than 2, say, the space has no complex structure, at least no useful one that I know of. And yeah, okay, so here's what it is. This first definition is maybe not so useful, but it's a definition. But maybe a nicer way to think of it is the moduli space of n-dimensional flat tori. Okay, so what does it mean? A torus is product of n copies of S1, and then you look at all the possible flat Riemannian metrics you can put on it. Okay, that's just, you can identify the points of this with tori with a flat Riemannian metric on it. And there's no sort of algebra here. I'm just saying it that way so that it looks a little more parallel to what happened for SL2. And it'll be helpful to me on the next slide. Okay, now what's kind of distinguished about these spaces among Riemannian manifolds is that they are highly symmetric in the following sense. So they have not self-maps, but self-correspondences. So multi-valued functions, which takes in a point and it spits out several other points. So I've just said how this works in the case of GLN. A typical example, you can take in a flat torus and you can spit out all its double covers. Okay, so there's maybe 2 to the n minus 1 of them. Each one of them comes with a Riemannian metric inherited from down below. So you've taken in one point and produced several. And these operations play well with the metric. That is, if you move your input point a little bit, all of the output points move by the same amount. So it's kind of locally isometric. So although they're multi-valued, these things which are called Hecke operators act on any, they commute with one another, and they act on any kind of linearization of the space. So the space of functions or the space of differential forms or cohomology or K-theory. So you have these commuting operators on those, and it's tempting, at least, to diagonalize them. So all right, here's my crude definition of an automorphic form. Okay, and it's sort of pretty close to the truth. So an automorphic form is going to be a differential form on this manifold. That's an eigenfunction of all Hecke operators. Okay, and although it's not obvious, we've seen 2 examples already, which is G4 and omega. Okay, that's what I call h of z dz. So in the 2 examples, the functions that showed up were modular forms for SL2. And here I'm lying a little bit because G4 was a quadratic differential and not an actual differential. So I should allow some vector bundles in the picture as well, and I'll just, for the purposes talk, I'll kind of just gloss over that. Okay, so for us, an automorphic form is, for a group, there's some canonical Riemannian manifold with some symmetries, and an automorphic form is a differential form that is an eigenfunction for those. Okay. So here is one of the first things that Langlands conjectured on the basis of his study of Eisenstein series. Okay, so this is from his book Euler Products and Eisenstein series, and kind of, I think, started the whole ball rolling. To an automorphic form on a group G and some algebraic data. Okay, that's a representation of the Langlands dual group. I'm not going to make a huge deal of it, but you need it. To that, you can associate an L function. So I want to take that as a black box, but let me say, in what sense is that a conjecture? So, from a historical point of view, I think all the examples of things that behave like a zeta function were suddenly unified by this definition. But when he defines what this L function should be, so what does it mean? He writes down the series for it. Okay, and the way that the form enters is that the coefficients are extracted with how these Hecke correspondences act on it. Okay, so but he writes down the series, but there's no way that series, just looking at it, you can't see any good properties. Okay, you can't see that it has an analytic continuation or a functional equation, or the series is, in most cases, except very, very simple ones, totally useless. So the only way to try to understand anything about it is to extract this L function from the form in some more direct way. And what I mean by that is something like in examples A and B, where you're going to maybe integrate the form over something and extract something nice. Okay, so that comes to, I'll distinguish 2 types of periods, and then I will talk about them in turn. Okay, so phi is an automorphic form on G, so some function or form on this Riemannian manifold. Okay, automorphic periods. If you have a subgroup of G, you get an inclusion of the sort of space for H in the space for G. And I'll define the automorphic period to be just the integral of phi over that space. Okay, that's a very general definition. It's not always going to give something useful, but let me just, okay, H, this space could be a point. All right, so as an example, this thing I said earlier of evaluating G4 at I actually falls in this framework. The group G is SL2, and the group H is the standard SO2, the stabilizer of x squared plus y squared. So if you work out what the space associated to this H is, it turns out to sit inside SL2 exactly. It's the point I when you think of the space for SL2 as the upper half plane. Okay, so point evaluations are sometimes included in this definition. Okay, so that's an automorphic period. The second thing is meant to kind of generalize example B, where I was integrating a differential form. So suppose you have a differential form that comes from cohomology. So that is to say, the harmonic representative for a cohomology class. That might seem very special, but it has a kind of role of distinguished importance, which I'll come to later. But a cohomological period, I mean, I allow myself to integrate this over any cycle. So any j-dimensional thing with no boundary. And that's what happened in example B. Now, just to be clear, in example B, there was a path that goes from one point to another, but it's at least it's a cycle relative to the boundary. Okay, so I'm being a little bit sloppy, but. All right, so these are two general constructions that specialize to A and B. And what I want to say in the rest of the talk is what their meaning is. I mean, some sort of theory about these. Okay, these two definitions, neither is contained in the other. Okay, in the first definition, the automorphic form is arbitrary, but you integrate over a very special type of object. In the second definition, the form is very restricted, but the cycle is more or less arbitrary. But sometimes they can overlap. Okay, in example B, I'm not going to explain this, but it is a case where they overlap. That is, you can see an integral in both ways at once. Okay, so the sort of story of the rest of the talk is most of the time I'm going to talk about one, that is the automorphic periods. And there I want to, as I said, present the work of a great many people over the last 30 years to say why this is sometimes related to L functions. Okay, and so I'll sort of try to clarify what sometimes and related exactly means. But in the end, there's going to be some sort of very beautiful general formula. Okay, that's the second thing, and that's going to be more speculative. I'm going to suggest some relations of it to motivic cohomology. And then when the two overlap, that overlap is going to be related to Beilensen's conjectures that relate special values of L functions to motivic cohomology.
When you say overlap, do you mean the automorphic
Yeah.
form is harmonic?
Yes, I mean, the automorphic form is harmonic, and moreover, the cycle it's integrated over is represented by one of these spaces H. Okay, so in other words, the first thing restricts phi. The first thing restricts the integration object, and the second thing restricts the automorphic form, and they overlap when both of those are restricted. And so it's actually, yeah.
For SL2, any automorphic form is harmonic, right?
Not in the definition I gave, because, for example, there are many functions on this space, just L2 functions. So yeah, maybe one thing I should clarify is, in this definition, there's a vast world of automorphic forms that are essentially transcendental in nature. So there'll be many functions in L2 that bear no known relationship to arithmetic. Okay, that's one of the reasons why these cohomological forms play a distinguished role, because they are related to arithmetic. Okay, so any other questions?
They all relate to arithmetic.
No, I didn't say I just said we don't know. No, I'm just saying, I said we didn't know. We don't know. I don't say they're not related. Okay, yeah, but anyway, this automorphic period part of the talk applies equally to transcendental or not. It makes no distinction. Okay, this is kind of a just to be kind of a nitpick. So you have to, when I integrate, you want to have a measure. There's a measure on everything in sight, which is Tamagawa measure. Also, and I think most people could probably safely ignore this, but there's an issue of how you normalize this form. Usually, you're not gifted with usually a form. In the examples before, I wrote down some formulas, but usually a form is given to you in a way that's unique only up to scaling, so you want to have some way to normalize it. So there are many ways you could do this depending on what you want to do, but I would say the simplest way, which sort of covers a very large number of cases, is to normalize it by L2 norm. Okay, if it doesn't converge, then maybe you have to do something different. But this is okay. Even normalizing it by L2 norm, it's still ambiguous up to phase, absolute value 1. So you can So I square the corresponding periods. Okay, I think you can ignore that point. But second point is that the simplest case of this story is when the group H is equal to the group G and the function phi is constant. And in that case, you're just integrating, in other words, basically the function 1 over G, and the period, according to my definition, is just the volume of G. So the period evaluation comes down to the evaluation of the Tamagawa number. So morally, I'll say what that means. You can think of these period formulas as being a generalization of this Tamagawa number story from the constant automorphic form to all the rest. Now, morally, because this constant automorphic form has many sorts of degenerate behavior, if you take what I say in the next slides and specialize it to the constant thing, everything will diverge. Okay, but still, I think I'll use this as it's a useful metaphor to keep in mind. Okay, so I'll refer a few times to Jacob's talk just to compare the situation of these periods with the situation of the Tamagawa number, which at least in a number field was developed a long time ago. Okay, so the first thing I want to say, just to remind you, you take a form on the space for G and you integrate it over subgroup H, and usually, that is if you just pick a group and some random subgroup H, we don't know of, and probably there isn't any kind of formula for H. But in a very large class of cases, there is. So we'll come to trying to clarify what that class is. But there are certainly many examples. So there are many, many examples in the literature of formulas like the following. So you have on the left-hand side a period of an automorphic form. On the right-hand side, you have a product of values of L functions, a product and ratio. Oops, sorry, in the denominator I switched. The add should be a subscript and the phi should be inside. But anyway, in the top, it's a product and ratio of L functions associated to the automorphic form phi. What changes in the various factors are what the representation of the dual group is and where they're evaluated. In the denominator, the representation in the dual group, the denominator is universal. The numerator varies from example to example. In the denominator, the representation of the dual group is the adjoint representation. All right, we're going to try to say what many examples mean, but there really are many. So I'm going to talk about this. So the examples A and B, which I gave earlier, fall into this framework, taking H to be SO2 or the diagonal torus inside SL2. So this is some, so on the left-hand side, you have an integral of something modular on the right-hand side. So, all right, so we want some sort of unified theory of formulas like this. And one thing I should emphasize, why do we care about formulas like this? They're also often you can somehow canonically take a square root. So as it stands, these are a primary way of accessing L functions over number fields. Okay, so say over a function field, the story is, there's no reason it should be so. Over a function field, the Grothendieck Lefschetz formula allows you in a way to just understand the L function directly. But over a number field, except in fairly simple cases, the only way we can really know how to access L functions is by passing through a formula of this type. And sometimes maybe you can, certainly for example, to establish any of the basic analytic properties. And maybe you can overlook this because some of these formulas are quite simple, but nonetheless, this is our primary way of getting at least analytic information about L functions. All right, so what am I going to say? I want to give you I want to give you a list of examples, mainly just to convey the amount of effort of many people that has gone into building this picture. I'm going to say, I think outline the methods known of proof is too strong. I'm going to say a bit about methods of proof. And I want to talk about what this squiggle means. Okay, so it means it's equal up to some junk, but there's also now a sort of way to replace this with an exact and very elegant formula. So I'll say that. And then finally, what is some unified way to talk about many examples? Sorry, are there any questions? Okay, sorry, could someone tell me the time? Ah, there is. Where?
In the corner of the 2:35. It's about 2 minutes.
Oh, there, okay, all right. Okay. Yeah.
So in the formula,
Yeah.
the EPS is a big particular value.
They vary also from example to example.
No, but if you mention the analytic problem, you should use it.
Yeah, so in that, okay, you're absolutely right. There are formulas where there's an Eisenstein series, and then varying the Eisenstein series in the phi shift the S. That's one way to say it. Okay, so this slide I'm not going to talk through, but I just want to say, as I said, I'm sort of summarizing the work of a lot of people. The classical cases, there's Hecke was the first person to recognize that you can attach an L function to a modular form. Okay, and that amounts to the case where H is the split torus and G is PGL2. The case of a non-split torus in PGL2 is much harder and was done much later by Waldspurger. The Rankin-Selberg theory, which is from the 1940s, is also an example of this story. And now, just so I could have a manageable list, I just picked a few examples in the case where the ambient group is GLN. Okay, okay, I won't talk through them. This is what happened. There's a generalization of this for any n due to Jacquet, Piatetsky, Shapiro, and Shalaika, and that was how they proved the basic properties of the standard L function attached to GLN. Okay, I've given some more examples. Maybe one thing I'll just point out to you is that if you take the orthogonal group, there's no known or expected formula for the period. We'll get to that in a second. And I mentioned the last case just because it's a particularly rich case which has been studied a lot. So they're very. So in all the examples, the first two examples, in all those cases, there are formulas of the type that I said. That is, the integral of the period is equal to some known L function. In the last case, it remains conjectural, but there's a lot of progress. I mean, maybe this paper of Ginsberg, Zhang, and Rallis is the closest to that, but the actual formula still isn't known. Okay, this is, anyway, just meant to give you, there's a very large and somewhat.
They are not known.
Yes, that's what it means. There's no known expression in general for this in terms of L functions. If you look at special cases where you can compute it explicitly, like Eisenstein series, it looks very unlikely that such a thing would exist. It's not to say that it's not interesting, but there's no formula in terms of L functions. Okay. Some methods of proof. Actually, before I say this, this is, I think, a good slide to kind of discuss the comparison with the Tamagawa number story. When I say Tamagawa number story, I mean the story over number fields. So now we've seen over function fields, there's now much more direct and conceptual proof. But over number fields, the way the Tamagawa number was evaluated, okay, there were many cases evaluated in the 19th century. But the sort of modern proof is a two-step proof, which goes like this. Langlands and Lai evaluated it in the case where the group is quasi-split, and then Kottwitz used the trace formula to compare any group to a quasi-split group. So one of the sort of paradigms for studying these automorphic periods is very similar. So on the one hand, there's something called the unfolding method. Okay, and so you can see the work of Rankin and Selberg as the first example of this. Whatever it is, let me just say that it often works when there's much more to say, but when there's some good notion of Fourier expansion of an automorphic form. And in fact, the work of Langlands and Lai has a very strong affinity with this unfolding method. On the other hand, the Kottwitz part of the Tamagawa number story also has an analog here due to Jacquet, and maybe I can single out Jacquet as someone who did somehow push the subject forward enormously in the 90s. So he developed an analog of the trace formula, so the usual trace formula, it's very complicated, but you can compare usually two groups in an effective way. The relative trace formula of Jacquet compares periods on two different groups. Okay? So now if you put 1 and 2 together, So there's sometimes you can evaluate, sometimes you can compare it to another group. You can access a large class of periods. Unlike the Tamagawa number case, it's not at all clear this strategy will access all periods. Okay, just for an explicit example, if you want to compute Fourier coefficients of automorphic forms on, say, E8, I think there's no strategy that we know of. There's a conjectural formula, but there's no strategy for attacking it, even conjecturally. Okay, but anyway, this allows you to access a fair bit. Now, right, the next thing I wanted to talk about is the squiggle. And again, I'll kind of make the comparison to the Tamagawa number story. So before Wei introduced the Tamagawa number, there was the mass formula. And the mass formula said that the mass, so some count of quadratic forms in a given genus, was a product of zeta values. And Jacob wrote an example of such a formula at the start of his talk. Okay, that kind of corresponds, as I said, to the case where phi is the constant function. And it was a product of zeta functions, and then there was some stuff, like powers of pi, values of gamma functions, and so on. And in general, that stuff is quite hard to compute. Okay, for example, if you take a quadratic form that has 2 dividing its discriminant, usually when you try to compute it, you decide to do something else. So, all right, this formula is kind of at a similar stage. Okay, this is kind of the analog of the it's a formula relating it to L functions, and there's a bunch of pi's, gamma functions, and other rational numbers there. So what was discovered, I would say, originally by Waldspurger, and then and it was understood by Ichino and Ikeda that it should somehow be applicable much more generally, is that you can, if you're willing, so just as Wei and Tamagawa introduced a sort of more complicated measure which made the statement much more conceptual, there's a similar thing here. So there's an exact formula for this which works in very many cases, which says that, so I'm going to introduce some much more conceptual substitute for the right-hand side. It still has the issue. If you want to compute an example, you still have to go and compute. But it somehow makes the conjecture it makes a much clearer conjecture. So here's the conjecture, and then I have to explain. In many cases, I'll have some text saying what it says. With prior normalizations, the period squared is, okay, and as in the Tamagawa number story, to make this more conceptual formulation, I have to introduce the Adels. Okay, so it's an integral over h of Adels of this inner product, h acting on phi, inner product phi. So here, to make sense of this, you have to pass to the adelic quotient. Okay, but once you do that, the conjecture becomes extraordinarily clean. And when you compute this integral, I'm going to say there's going to be some more text here, but when you compute this, what you'll find is those L functions dropping out, plus when you have to compute something at every place, and then at a few places you'll get the junk that you see earlier. But in this form, it's a clean conjecture. So let me add some technical notes about it. Okay, so this is more directed at experts. But firstly, on the right-hand side, you have a product of matrix these integrals. What will happen whenever it works is that the local integrals will converge and the adelic integral will not. Okay, so the way you make sense of it is each local integral almost everywhere is a local factor of an L function. That's how you make sense of the global integral. But the formula seems to be correct, as far as I know, in every setting. So here are the conditions. Phi is everywhere tempered. You have multiplicity 1, maybe, and all the local integrals converge. Again, those are some technical settings, but in many cases, there's this universal formula. And this Q, okay, so for Tamagawa numbers, there was also a rational number, which was, for example, 2 for SON. Here, what it's conjectured to be is the inverse of the size of the Arthur component group. So this is a rather extraordinary conjecture because it replaces a kind of a large class of formulas with messy stuff in them by a very clean one. Of course, the work is hidden, but...
Did you explain what H small is?
Sorry?
Did you explain what H small is?
H.
No, lowercase h.
Okay, it's an integral over this adelic group, and little h is a variable in here. that okay?
What's H times I?
Okay, yeah, so I didn't explain this. Let me I'll say, so you can treat any function, in fact, on G, you can actually treat it as a function on an adelic quotient. Okay, so if you have a function here, let's say, let me just talk about functions. You can think of it as a function on this bigger space. Here you have an inner product, an L2 inner product, and you also have an action of this adelic group. So that's what H phi means. It means the action of this group restricted to H. It's a shift of phi. So I'm sorry, I know if you've never seen this, this right-hand side looks just, incomprehensible. But you can take my word that at least it's a clean formulation, and when you unwind it, you'll get the previous thing.
Kind of out-relation function?
Yeah. But it's difficult to have too much direct intuition because the whole integral doesn't converge. You have to do it place by place and take a product. Yeah. So are there any other questions about this? Maybe you could make up a case. Yeah, I'm sorry. Maybe you could make up. No, but I don't. So usually it's either in the middle of the critical strip, or the local integrals diverge. So off the top of I don't really know, but off the top of my head, I don't actually. I'm not sure of an example. Certainly in all the interesting cases, the cases you're most interested in involve central values, and it's as convergent as a central Euler product. Okay, so now I've given you this list. I sort of hinted at this list of examples. And for a long time, I think it's been generally understood what features. So interesting example, what it means, where are there such formulas for what G and H? And for a long time, I think it's been sort of morally clear, but it's become a little bit more precise recently from the work of Yanis Sakellarides. So let me say a bit about that. Most cases where this period on G, so you have a pair G and H, you're integrating forms on G over H. So it's been, I don't know who it's due to, but I think it's been understood from the very start that the existence of such formulas has something to do with multiplicity 1. Okay, and an algebraic incarnation of multiplicity 1 is the notion of spherical. So a subgroup H in a group G is called spherical if it acts with open orbit on the full flag variety, G mod Borel. Okay, that's an algebraic definition. So speaking a bit crudely, most examples where there are such formulas are spherical. Converse is not true. Not every spherical pair gives such a formula, but one direction works. And then the situation really improved with the work of Dennis Gates-Curry and David Nadler, because they showed, at least under some conditions, to a spherical pair, G and H, that is, G is a reductive group, H is a spherical subgroup of G, you can attach, I said this in some clumsy way, you can attach a dual group to the pair. Okay, so a basic construction in the Langlands program is a reductive group has a dual group. Okay, but Gates-Curry and Nadler found a natural way to attach a sort of dual group to the pair G and H. It's a subgroup of the dual group of G. It has nothing at all to do with the dual group of H. Okay. So that's very good because it gives you the possibility of having some sort of systematic way of fitting these pairs into the Langlands program. And in fact, what seems to be the case is the study of the H periods, they should be part of a kind of relative Langlands program which takes as the basic object a pair of a group G and a spherical subgroup H. Okay, and the point of this is that, so the questions and answers to that will be phrased in terms of this relative dual group. So the global question is, can you give a formula for the automorphic for this period? And Sakellarides, who's the person who's done most of the work on this after Gates-Curry and Nadler, has proposed a candidate conjecture for the formula. Okay, so I said earlier that the H period is some product of L functions. I didn't say which, so to speak, which L functions, which points. He describes a conjecture for that in terms of the dual data attached to this pair. So that, okay, so it's starting to look like a universal statement. There's still a long way to go. But anyway, to have so this is kind of a little parallel track to the Langlands program, okay, where you deal with pairs instead of groups. And it also has a local prong, which I'll say. So for example, the Langlands program predicts, for example, the representation theory of a group over a local field. And one thing this relative version Langlands program would predict the relative representation theory. Okay, so it gives you a prediction for which representations of G occur in G mod H. Okay, and that's now described in terms of this relative dual group. And some evidence of that was worked out in a paper of mine and Yanis. So one thing I want to say, there are, as I said, many examples, and it's difficult to sort of have one single framework that captures all of them. So in particular, one failing of this is it doesn't capture theta functions. But it seems at least that it captures a lot of interesting examples under one roof and gives us some direction for a theory of this. Okay, so that's all I have to say about automorphic periods. Or let me spend the last few minutes on, where'd it go? Oh, there it is. Okay, on the cohomological periods. And so my discussion of cohomological periods will be much more speculative. Okay, I have a little bit of evidence for what I'm going to say, but you should take it with a grain of salt as it stands. So, all right, what does it mean, cohomological period? We want to understand now integrals of automorphic forms, but of a special type. So they arise from cohomology. You take a cohomology class for this Riemannian manifold, and you represent it by a harmonic form. And now I ask what its integral over any cycle is. And I ask that because it seems like it'll have an interesting answer. But the difference is this cycle doesn't have to have any group theoretic structure. Okay, it's just any closed thing. And these cohomological forms somehow, so in the grand scheme of automorphic forms, they're a tiny little thing. But they play a very important role because they are all of algebraic nature. So as we were saying earlier, some automorphic forms have no known relation to the world of algebra, the Galois group, and so on. The cohomological ones do. So they kind of live at the intersection of this Langlands program and the arithmetic part of the Langlands program. So that's one reason why they're somehow distinguished in their importance. And they allow you to compute this, in other words, they're computing the cohomology of this manifold, which you can also think of as the group cohomology of this arithmetic group. Okay, so let me say a little bit about what we know, which is not very much. When the group has no algebraic structure, so in the case when the space for G has a complex structure, which is called a Shimura variety, then there's, I think, at least reasonable guesses you can make about this. Okay, and I don't want to, so Shimura, for example, already formulated conjectures for GL2, and Michael Harris proved some part of those. But I'm more interested in the orthogonal case where there's really no algebraic structure. And there it's very little, so I said that these cohomological periods sometimes overlap with automorphic periods. But other than that case, which sort of falls under the previous umbrella, this has been very little studied. And the kind of degenerate case of this, when you take phi to be somehow the constant automorphic form, it's related to the theory of the Borel regulator. And that's the only case I know where there's a significant study of this. Okay, so I'm going to switch to a different viewpoint, because which is a little more elegant. So if you have a Riemannian manifold, let's say a compact Riemannian manifold, these aren't compact, but the things I'll say will still make sense. If you have a compact Riemannian manifold, its cohomology has a metric on it. If you have a complex cohomology class, you could represent it by a harmonic form, and you can compute its L2 norm. Okay, so what that means is, you take ignoring this compactness issue, this guy, at least mod torsion, everything I say will be mod torsion, so I apologize if I forget to say it. This guy, mod torsion, has a metric on it, a positive definite quadratic form. And if you unravel what that means, okay, well, what does this metric measure? It computes exactly this type of integral of harmonic forms over cycles. Okay, it's a symmetric matrix related to this period matrix. So I'm going to switch to this viewpoint, which is kind of a nicer way of formulating everything, which is which lattice with a metric is this? Okay, the cohomology of this has a metric, and okay, the lengths of vectors there are certainly not rational, they're just some real numbers. So which real numbers are they? So, okay, now I'm going to give some caveats aimed at experts, so just to restrict the scope of what I'm about to say. Phi in what I'm about to say should correspond to an irreducible Galois representation of geometric origin, which is valued in the dual group. And, yes, what am I talking about? Irreducible. Yeah, the important word here is irreducible. So by that I mean the centralizer is finite. And I've put that word in because, in fact, this rules out examples to do, for example, with the trivial automorphic representation. Next, I'm not going to look at the whole cohomology, but just the part of it that's relevant to this representation. I'll put a 0 there. Okay, to a first, again, you can ignore that. And the most important caveat is, I'm going to make some speculations, but they should certainly be considered only up to commensurability. So I'll say two lattices are the same, but really the best you can hope for is that they're the same up to finite index. Okay, so here's the cohomology. As I said, if you don't, it's localized, but you can ignore that. Let Q be the smallest degree in which that cohomology is non-zero. Okay, so what happens is it's sort of, this cohomology is non-zero in some range around the middle dimension. Okay, so here's I'm trying to describe the structure of this thing as a lattice with a metric. So here's the conjecture. There's an isometric isomorphism. Okay, so from this lowest degree cohomology, tensor an exterior power of some fixed lattice L, which I'm going to tell you about, with the Q plus ith cohomology. So in other words, this describes as a lattice with metric any cohomology group in terms of the bottom one. And actually, the situation's a bit better. So it looks like it just describes one in terms of another, but it does a little more than that. What is L? So L, I think, should be, so we saw earlier in the talk this L function, it's the adjoint L function of phi at 1. Beilensen's conjectures relate that, predict what that is in terms of a certain motivic cohomology group. Now, it's possible to put a metric on this motivic cohomology group once you pick some polarization on a certain Hodge structure. And so, okay, so that's what this L should be. Okay, so there's some specific candidate for it. And okay, so it looks like this is relating the cohomology groups in two different degrees. But in fact, it does a little bit better than that because you also know Poincare duality. And if you add that in, at least if the dimension of cohomology in lowest dimension is 1, it actually predicts exactly what this metrized lattice is. Okay, everything is up to commensurability again, but so somehow knowing Poincare duality allows you to not just say what one is relative to another, but exactly what they are. So this amounts, if you unravel it, to some predictions of what these cohomological periods should be. Okay, so what's the evidence? So in a few cases, Karthik, Prasad, and I have checked that this is compatible with automorphic conjecture. So let me say what that means. I said sometimes cohomological periods and automorphic periods coincide. Now on the previous, this conjecture is somehow completely of a different nature to what you see in automorphic conjectures. So now we haven't checked so many cases, but the ones we look at, the conjectures match up. And by that I mean they match, their equivalence reduces to Beilensen's conjecture. Okay. In some cases that have extra symmetry, you can check this, and every say check, I mean, it's again conditional on Beilensen's conjecture. You can check something non-trivial about this using analytic torsion. So you can actually check this, that it's true on Beilensen's conjecture. Not just that it's compatible, but it's true. But those are some small cases with extra symmetry. So I would really like to have numerical evidence for this, which I think is which is not so, everything is actually computable. So, but it seems like it'll take a long time. Now, let me say something sort of algebraic. So if you look at the way I stated it, it suggests that the exterior algebra, this exterior algebra on this motivic cohomology group acts on the automorphic cohomology. So it sort of suggests that there are some extra operations on the cohomology of this arithmetic group, which are in a way indexed by these motivic cohomology groups. So I have no clue at all what that story might be. I mean, those two things live in different worlds. But if you ignore the relationship to motivic cohomology, at least one can think of a natural candidate for what these extra operations are, which is that the usual Hecke algebra acts on cohomology, but you can also look at a slightly more derived version, and then it'll act on cohomology shifting degrees. And it's plausible that I don't know, but it's plausible that accounts for these extra degree shifting operations. All right, so that's all I have to say. Let me just summarize the main points of the talk. So as far as automorphic periods, I think we're within sight of a, not there yet, but within sight of a sort of universal formula which should be comparably clean to Tamagawa number equals 1. Probably not as short as Tamagawa number equals 1. But a proof really doesn't seem in sight. That is, the known methods of proof are some. Okay, as for cohomological periods, I think that they suggest this relation between these very specific motivic cohomology groups, that is, of adjoint motives, and the automorphic cohomology. And as I said, I have no clue of what a conjectural mechanism might be. I just have some sort of anecdotal things which you can measure, which seem to be the same. Okay, thanks.
Can you say a few more words about how analytic torsion comes into these
Yeah,
calculations?
let me just I'll say one very brief thing. Analytic torsion gives you it gives you one piece of information about the volumes of these lattices. It gives you exactly one constraint. And I arrived at this conjecture by trying to understand some algebraic structure that would be compatible with that. Okay, so yeah.
Can you show the next slide? No. Just the definition of shell.
Yeah.
Can you say more about what you mean by derived version of thing?
Yeah. So let me say this is in the not in the world of things I've checked, but it seems plausible. That is to say, the usual Hecke algebra at P. So this is a plausible candidate for which. So you can look at the usual Hecke algebra at P. You can define as homomorphisms as modules over a p-adic group from, let's say, the group algebra of this quotient to the group algebra of this quotient. Okay. Now you can make this into an ext. Okay, you can look at all the exts. And the higher exts are torsion, but anyway, they still act on the automorphic cohomology. And then somehow out of that only gives you torsion operations, so there's some issues still, but I think you can build things out of those.